Discuss the MCQs. In which of the following pair does the metal have different oxidation number? So if we check chromate, um, CrO4 with a charge of 2 minus, each oxygen is minus 2. So 4 will be minus 8, chromium should be plus 6. In a dichromate, Cr2O7 with a charge of 2 minus, each oxygen is minus 2, so 7 will be minus 14. This will be plus 12 because the net is minus 2, so each will be plus 6, here plus 6. So they have identical. If we check this already, we check CrOCl3. CrOCl, and the charge is minus 1. Each chlorine is minus 1. We always start with the most electronegative. Each oxygen is minus 2, so 3 will be minus 6. And when two more electronegative elements are there, here chlorine is group 7 minus 1. So chromium is, because the net charge is minus 1, so the chromium should be plus 6. So this also chromium is plus 6. When we check V2O5, each oxygen is minus 2, so 5 will be minus 10. And vanadium should be plus 10, so each will be plus 5. In VO4 with the charge 3 minus, each oxygen is minus 2, 4 will be minus 8. So this should be plus 5. So it means that D will be the right answer because or rest all of them we worked out that they have the same oxidation number. So in D it should be a different oxidation number. This question is about the reaction. Iron 3 reacted with titanium to form iron 2 and titanium. The electrode potential for the system for iron 3 to iron 2 is 0.77 and the cell. What is this electrode potential of a titanium? Look, the formula is that it's a cell. So remember redox, reduction minus oxidation will be equals to the cell, electrode potential of a cell. So reduction, iron 3 become iron 2. So that is a reduction electrode potential. Don't bother about the numbers which are written here, okay? Like it can be 2, it can be 3, but you don't have to bother about these numbers. You always take for individual 1 mole. It's always irrespective of the what equation is there. So electrode potential for this one is 0.77 minus oxidation. Iron titanium is being oxidized. We don't know. And what is the electrode potential of a cell? 2.40. If I need X, so 0.77 minus 2.40, that will be equals to X. So 0.77 minus 2.4 is equals to X. What is the value for X here? 0.77 minus 2.4. So X is equals to minus 1.63. So we'll write here B minus 1.63. Is it clear how we worked out the electrode potential? Next, we have part B. What metal should be used for the electrode in this? How to identify which metal should be used? Iron 2 to iron 3. Look, there is a change. There is only a change in oxidation number, but it is not forming atoms or atom is not turning into iron. So when only ions are changing within the electrode, we use a platinum electrode. Like this, because the ions are changing their oxidation number means the solution is changing. And titanium ion turning to titanium atom is there, so titanium is formation is there, so we should use a titanium. So the electrode, so how we decide which electrode we should use? If you find that only change of oxidation number is taking place, ions are changing their oxidation numbers, then we use a platinum electrode. But if you find that atoms are being formed or ions form atom or atom form ions, then you should use an electrode of the same metal. So we use a platinum and titanium. So C will be the right answer. The half cell for iron 3 to iron 2 electrode system is prepared by mixing equal volume of the solution of iron 3 sulfate and iron 2 sulfate. What concentration of the original solution are needed? Whenever we start a reaction, we want the concentration, like we want the same number of the moles or the equal concentration, equal should be the equal volume of a solution are used. So we want the same number of moles for iron 3 and iron 2. This compound FeSO4, when it will decompose, it will give us iron 2 ion and it will give sulfate ion. And when a compound Fe2SO4 in a bracket 3 will decompose, it will give iron 3 ion and it will give, and how many iron 3 ion? 2 iron 3 ion it will give. And it will give a sulfate ion, 3 sulfate ion. But our main concern is producing equal amount of iron 3 and iron 2 in the solution. So if I need the equal amount, but one molecule is giving twice the moles than other. So if I use 1 mole and 0.5, like if I use 1 mole of iron sulfate, I'll get 1 mole of this. And if I use 0.5 moles of this, Fe, because it's written here. And remember one thing, the moles equal concentrations times the volume. Okay. And we are mixing the equal volume, the same volume is there. So I want the same number of the moles. But if I mix the same volume of this, if two solutions are there, like let's say I took 10 cm cube of the two solutions. So I need the same number of the moles of these two solutions as well. If I have like 0.5, or let's make it very simple. Let's say I'm using, because we want the solution to have a concentration of a 1 mole per dm cube. That is what we want. Okay. So we want the solution, the standard solution should be 1 mole per dm cube. So if I want to make a solution of 1 mole per dm cube, like 1 dm cube, so how much should be there? This will be 0.5 decimeter cube and this will also be 0.5 decimeter cube. Because when I mix them together, the total volume of the solution will be 1 decimeter cube. Now, and I want equal, like I want the concentration of the two solutions to be 1 mole per dm cube in the solution. So if I use the concentration, the original concentration of this one is 1 mole per dm cube. So how many moles will be there? How many moles of this one will be there? In the first one, it will be 0.5 mole. Because the concentration, or if I use the concentration 1 here, and the volume is 0.5, so how many moles will be there? So concentration, so 0.5 moles will be there. And when I work out the concentration here, if I'm using a concentration 0.5 mole per dm cube, so 0.5 multiplied by 0.5, so what I'll get? I'll get 0.25, because concentration is moles multiply, moles is concentrations times the volume. So 0.5 times 0.5, 0.25 I'll get. But when I mix them together, now the concentration of the solution will not be 1 mole per dm cube. You got it? Like for why A is wrong? Because I'll not get the same amount of iron sulfate, concentration 1 mole per dm cube, and same amount for iron 2 sulfate, iron 3 sulfate. So it cannot be A. If we check with B, because again, B is not giving. But what about C? In C, if I use the concentration, in C, if I use the concentration 2 mole per dm cube. So what will be the moles here? How many moles I'll get? I'll get 1 mole. And now what is this concentration of this solution? Because if I have 1 mole in 1 dm cube, so concentration of this solution, new solution will be 1 mole per dm cube. Like the new concentration as we mix them together. And if I have iron sulfate and I use 1 mole here, the concentration 1 mole per dm cube. The concentration of iron is 1 mole per dm cube, but because if I have 1 mole per dm cube iron 3 sulfate, its concentration will become 2 mole per dm cube. Why 2 mole per dm cube? Because 1 mole of iron 3 sulfate gives 2 moles of iron 3. So the overall number, how many moles I will get? I will get 1 mole. And 1 mole divided by 1 dm cube, so again I'll get the same concentration. So if I use the original solution of iron 2 sulfate as 2 mole per dm cube concentration, and I use the iron 3 sulfate solution as 1 mole per dm cube, when I mix the two solutions, I will get the concentration for each solution as 1 mole per decimeter cube. The concentration of each iron 3 and iron 2 will be 1 mole per dm cube. Is it clear? Should I repeat? Is it clear or should I repeat? Yes, look, the concept is that whenever you mix the two solutions, yeah, sure, I'll repeat. Look, the concept is that when the final solution, I want the concentration of the final solution to be 1 mole per dm cube. I want both concentration to be 1 mole per dm cube in the final solution. Okay, that is what I want. Originally, we are preparing it by mixing equal volume of the two solutions. Let's say we want to make 1 mole, the concentration 1 mole per dm cube. So and I want the final solution to be 1 decimeter cube or 1 liter. So means I have to take half dm cube of this and half dm cube of this one. So 0.5 dm cube of this and 0.5 dm cube of this. Okay. If I take iron 2 sulfate, concentration 1 mole per dm cube. So if I take iron 2 sulfate with a concentration 1 mole per dm cube, this iron 2 sulfate will dissociate into iron 2 and sulfate ion. The ratio is 1:1. So if I'm taking the original solution, this is the original solution and this is the final. If original solution, I have a concentration 1 mole. So this will also have concentration 1. So the concentration here will be, let's say I'm taking 2 because C is the right answer. So if I'm taking 2, so this will be 2, this will also be 2. So the concentration of the iron 2 ion will be plus 2 mole per dm cube. So 2 mole multiplied by 0.5. So 2 multiplied by 0.5 means how many moles I will get? I will get 1 mole. Okay. When I mix this 1 mole here, so I have 1 mole and I have volume as 1. So what concentration I will get? Concentration will be 1 mole per dm cube. That is for iron 2. But for iron 3, which is forming Fe2 SO4 in a bracket 3, when it dissociate, it will dissociate into iron 3 ion and a sulfate ion. So if I take a concentration of iron 3 as 1 mole per dm cube, if I take the concentration of iron 3 as 1 mole per dm cube, what is the concentration of iron 3 ions? It will be twice. Why? Because 1 mole of this compound gives 2 moles of iron 3. So what is the original, what is the concentration of iron 3 ion? The solution concentration is 1 mole per dm cube, but iron 3 ion concentration will be 2 mole per dm cube because one molecule gives 2 iron 3 ions. And how many moles will be there? 2 into 0.5, so it will become 1. And then 1 divided by 1, what I'll get? I'll get the same number of, same concentration for iron 3 ion as well, which is 1 mole per dm cube. Is it clear? What is the electronic configuration of the chromium atom? So if you want a chromium atom, it's 3d5 and 4s1 is there. So 3d5, 4s1, it matches with A because half-filled orbitals are more stable as compared to a partially filled orbital. That's why chromium is 3d5 and 4s. This based on learning. the configuration, memorize. What is the volume of iron 3 used in? The volume was 0.5. Both we use 0.5. What we did was we use zero point 0.5 because we use equal volume. So we use 0.5 decimeter cube of this and we use 0.5 dm cube of this one. But when we mix them together, the total volume become 1 mole per dm, 1 dm cube. The concentration was 2 mole per dm cube here. Because if the volume is double, the concentration will become half. So here the concentration is 2 mole per dm cube. So when we double the volume, the concentration will become half. So what is the concentration of iron 3 ion? Iron 2 ion, it will be 1 mole. And here the concentration of a solution, we took Fe3, Fe2SO4 in a bracket 3. So it gives 2 iron 3 ions. So the ratio is 1:2. So if I use a concentration of this solution as 1 mole per dm cube, the concentration of the ion will be 2 mole per dm cube. So this is 2 mole per dm cube. But when we mix, it is double the volume, because if they are mixed, the volume will be double. So concentration will become half. So concentration of both iron 3 and iron 2 will be 1 mole per decimeter cube. Question 4, what are the ligands? They should have a lone pair, because to form a dative bond, they're giving that lone pair to that central metal atom. So when they give their lone pair to a central metal atom, so it is forming a dative bond. So they should be electron pair donors. They should be able to, it's not about charge, it's about they should donate their electron pair so that they can form a dative bond. So its charge might be there, may not be there, but it's always the electron, the pair which they donate to form a dative bond. Diamine, copper 1 ion are not colored because, so what could be the reason why it's not colored? The colored compound is due to the formation of like the presence of the d orbital, like partially filled d orbital, and the splitting. The d orbital in copper cannot split. It can split, but the main thing is the color. It depends on the empty d orbital. So in case of a copper 1 ion, the dd orbitals transitions are not possible, because when you write the configuration of a copper ion, so you will find that 1s2, 2s2, 2p6, 3s2, 3p1, like here, copper is 29. So for 29, the configuration is for 29, the configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. That is a configuration. But when the copper loses electron loss from the last cell, so 1s2, 2s2, 2p6, 3s2, 3p6, 3d9, and 4s1 is there. This electron, to make this stable, it jumps to 3d when copper 1 is there, so it becomes 3d10. When there's a 3d10, like d orbital is complete, when d orbital is complete, there's the transition is not possible. So that's why like it cannot absorb, an electron cannot absorb energy. As a result, the orbitals are full, so it won't show any specific color. Copper 2 ion form a complex with 2,3-diaminoethane, En. Name the type of a ligand. Look, amine group is there. How many lone pairs? Because each amine group, nitrogen group contain. So this is the structure. So each nitrogen group contains two lone pair. If there are two lone pair, what type of ligand is this? This will be a bidentate ligand. No, the transition element, it's when atoms are there, the definition of a transition element, they have either incomplete d orbital, they form incomplete d orbitals. They have incomplete d orbital, that is a transition. But zinc and scandium are not having incomplete d or like one is not having d orbital, another one is full d orbital. That's why we don't count scandium as zinc as a transition. What about the coordination number? Coordination number means how many dative bond it can form. So it's a bidentate ligand. Each En can form two dative bond. So if a bidentate ligand is there, coordination number means how many dative bonds are formed. So six dative bonds are formed. And what is the type of a ligand? It's a bidentate. So B will be the right answer. Aqueous sodium hydroxide was added to iron 2 sulfate. And if we iron 2 sulfate, it will form iron 3 hydroxide, which will be dirty green precipitate. How you know bidentate? Then you have to check an element. As they mention here, it's a diamine. Each nitrogen contain a lone pair. So it means there are two lone pairs in the structure because of the two nitrogen group. So it means that the two nitrogen group, they can use their lone pair to form a dative bond. That's why it is a bidentate. If it was a triamino, then it will be a tridentate. If it's only amine, then it will be a monodentate. So iron 2 is a dirty green precipitate, but when it is oxidized to iron 3, it will be red brown. So you have to learn this, the color of the precipitate formed when we add aqueous ammonia and the sodium hydroxide, as well as the formula of the precipitates. When aqueous ammonia is added to an aqueous solution of a zinc sulfate, a white precipitate form which dissolve in excess of ammonia to give a colorless solution. Formation of the reaction. So the formation of the reaction is always due to the deprotonation. The first reaction is so deprotonation is there, the first one. There means acid-base reaction, which we call deprotonation, in which what happened, like, let's say we were having a complex of a zinc. So this is a complex of a zinc with a charge of 2 plus. When we add aqueous ammonia, ammonia accept proton, that's called deprotonation, or you can say acid-base reaction. It will become ZnOH in a bracket 2 and NH3 in a bracket 4. And plus NH4 will be formed, two of them. So this reaction is always the first reaction is a deprotonation. Okay. The second is depending on what kind of like hydroxide it is forming. It dissolved to form a colorless solution. So further, how it can be dissolved? So if we have a zinc hydroxide is there, and sorry, I put ammonia here by mistake. It should be H2O because 4 water molecules are still left. Then if a precipitate dissolve in case of this is a PPT, and when we add an axis, ammonia might take position of both of them, so it will become ZnNH3 maybe in a bracket 6. So this is a ligand exchange. So first one is a deprotonation and the second one is a ligand exchange. And it is a fix, like for zinc it is fixed, for chromium it is a acid-base reaction again because it's amphoteric, aluminum also amphoteric. So you have to learn this. It's related to memorizing when zinc compounds reacted with aqueous ammonia as well as aqueous sodium hydroxide. Okay. Benzene is sometimes represented by a Kekulé structure. If there were the only structure of a benzene, what would be the total number of isomers of a dichlorobenzene? How many isomers could be formed of a dichlorobenzene? Dichlorobenzene means like two chlorine could be attached. If this was the only structure, okay? So what is the possibility? Maybe chlorine here, another chlorine here, that is one isomer. Maybe chlorine here, another chlorine here, that is another isomer. Maybe chlorine here, another chlorine here, that is another isomer. Maybe chlorine here and another chlorine here. That is the same isomer which I drew, because if I count this as 1, 2, 3, and it will be 1, 2, 3. So it's the same if chlorine attach on this side or other side. So how many isomers are possible? It means there are three possible isomers are uh, like here, or another one is when both chlorine might be attached to the same carbon. That is another possibility is there, because we want to draw isomers. So this is one. This is a second. Like I'll keep one place constant. I count as one, and then the second one I'm moving. So I have one, like first I have 1, 2 dichlorobenzene, or 1, 4 dichlorobenzene, or 1, 2, 3. Yeah. Sorry, 1, 2, and 3 is there. 1, 3 dichlorobenzene, 1, 4 dichlorobenzene, and 1, 2 dichlorobenzene. And yeah, this one is fixed. So with reference to that, if I attach here and count 1, 2, 3, 4, 5, 6. About 1, 1. No, the problem, if I try to draw 1, 1, then the benzene double bond will break down. But 1, 2, look, this 1, 2 will have two possibility, because look, it might be attached here or it might be attached here as well. That's why four isomers are possible. Like chlorine might be attached here, chlorine might. So these are the two different structure, because here the two carbon have single bond. They are 1, 2, and here two carbons are having a double bond, and this is also 1, 2. So how many possibles are there? It means four possibilities are there. Is it clear? So this 1, 2 and this 1, 2 are different. Why? Because they have a single bond, this have a double bond between them. What is the product when benzene react with fuming sulfuric acid? So HSO3 is formed. HSO3, which one is HSO3? So B. So it's a direct question which is totally related to mechanism. No, sulfur trioxide is there, sorry. HSO3, not OA. Because it will form HSO3. So either D can be an answer, or this is also HSO3. But it's not OH is there. It is like sulfur is bonded with a benzene, not oxygen. I did not check that one. So it should be D. Because sulfur directly bonded with a benzene, right? This is this sulfur, because it is adjusted with the benzene, right? That's why D is the right answer. Again, it's related to learning the mechanism. Here, hydrogen bonds are formed when methylamine dissolve in water. Which of the following best representation? It is important that when hydrogen bond is formed, if the bond angle is 180 degrees, okay, between the hydrogen, and the hydrogen bond is always formed between the lone pair And hydrogen should be directly attached to nitrogen or oxygen or a fluorine to form a hydrogen bond. So here, hydrogen attached to oxygen and then attracted toward the lone pair. This will be a hydrogen bond. But the mistake here is the bond angle is not 180. Here the bond angle is 180, so that's right because hydrogen bond is 180. This is wrong. Why this is wrong? Because this hydrogen cannot form a hydrogen bond because it is attached with a carbon. This, and here also this hydrogen cannot form a hydrogen bond because it is attached. The hydrogen here can form a hydrogen bond which is attached with nitrogen, but not because hydrogen directly bonded with oxygen, nitrogen, or a fluorine. That hydrogen is only capable of forming a hydrogen bond. In question 12, which type of compound cannot be a monomer in polyamide? So amide linkage are there or polyamides means many amine groups are together. We call them as a polyamide. But if we have already amide cannot form for polyamides. Like that's why A is the right answer. Like amide, if it is a amine reacted with acyl chloride or amino acid reacted with acyl chloride or so they will or amino acid react with ammonia or amino acid react with halogenoalkane, they will form amides. But because amide is C double bonded with O and N group is there. If amide is already there, then it won't be a monomer. Amide cannot form further amides. Amide is a linkage which is formed when carboxylic acid react with amine group. Alanine is an amino acid. Which structure best represent alanine at a high pH? High pH means like if we have more hydrogen, high pH means we'll have alkaline medium. Okay. In alkaline medium, because amino acids have acid group and amine group is there. If we have more alkaline, means as a result, this proton will be lost and the other one because remain is not able to further take its proton. So what is a right structure which it can exist? Because if you remember the existence of the amino acids, if we have one side amine group is there and another side acid is there, first in a neutral solution, this will lose proton, this will gain proton. So this will become N plus and this will become CO minus. This is what usually happen, like in a neutral solution. But now in the question, we have a high solution with a high pH. High pH means alkaline solution. So if we have an alkaline solution, this OH which was accepted by this one, this will also be lost. So this will be lost. So we'll have NH, no charge will be there, NH2, and this will remain negative. So B will be the right answer. Is it clear? If it was a low pH, then what will be our answer? In that case, our answer will be C. If there was, this is in a high pH alkaline solution, and if it's a low pH, then it will, C will be the answer. Alanine is a crystalline solid at room temperature. What are the main forces? Because these amino acids existing as an ion, and they will have ionic bond and strong attraction between the oppositely charged ions. Between the molecule, they will have high ionic bond. What are the bond stretches responsible for P and Q? You can refer to a data booklet. Bond stretching ranges are shown. This is usually due to Q is mainly because 1700 is there. It is usually due to carbonyl group. Why not London force? Is it not the main? No, it is existing as a solid at room temperature. That's why London force is it's not having too many electrons, but still existing as a solid. And a regular a structure, crystalline solid. So crystalline solid means regular structure. So regular structure can exist only in ionic compound or a giant structure. So that's why it is ionic. So when we check Q, C double bonded with O. Um, Aldehyde is 1740 to 1720. So, it's a very sharp absorption is there. So aldehyde or a ketone. This one aldehyde or a ketone is 1700. So it's not ketone, it's an aldehyde. And then what about the peak at P? Peak at P, when we check, it's around 28 or 2900. When we check the CH for aldehyde, 2900. So that's both matches with aldehyde. Is it clear? Next, we have question 15. How many peaks are there in a carbon 13 means like how many different carbon environments are there? That is carbon 13 spectrum, okay? Like how many different environments of the carbon? So if I check this one, this is CH3, this is CH, this is CH2, this is CH2, this is CH2, this is CH2, this is CH2. Now, if we check this one, it's three identical carbon are there. Like, because how many peaks are there in the carbon 13 NMR of a methyl cyclohexane? Carbon 13 peak, like carbon 13 peaks, how many different neighbors are there? So how we can identify the number of the neighbors? And this is this is a methyl cyclohexane. Okay. So for a carbon neighbors, it's not like four different groups are attached to a carbon. When we talk about the carbon, main is like identifying the type of the carbon atoms in this methyl cyclohexane. How many types of the carbon atoms are there? Are they identical? Even that is CH2, but is it identical to the neighbor? When I check this one, when I check this one, its neighbor is CH2, but overall all neighbors are different. And we need NMR, nuclear magnetic resonance. So it means this carbon will be different compared to others. When I check